Hello, my name is Paweł Sroka. I have the pleasure to present the results of my and my colleagues Adrian Klik's research entitled Distributed Learning for Vehicular Dynamic Spectrum Access in Autonomous Driving. So the plan of my talk is as follows. I will start with the short introduction to the motivation of our work. So I will explain the idea of vehicular dynamic spectrum access and its use for autonomous platooning. Then I will go to the description of the system model of consideration in this work, and I will outline the problem formulation, the mathematical description of the problem, and the details of the applied Qlearning solution. Later on, I will go to the simulation results section, where I'll present the comparison of the proposed Qlearning solutions with some conventional approaches, and I will end up my talk with conclusions. So first, with the motivation, our goal with this work is simply to improve the V2X communications, so vehicle to everything communications, in case of the platooning scenario, right? So we consider autonomous platooning, where the cars are steered by autonomous controller, known as the cooperative adaptive cruise control. And in such a case, of course, each platoon car needs to receive the information from the other cars on its mobility parameters and the behavior, expected behavior. So we should be able to receive the information from the platoon reader and the preceding car. Now, for such a scenario, the 3GPP envisaged quite high requirements for the 5G system, because the expected reliability of communication in such a case is between 90 to 99.99% of reliability, with the latter case actually applied in case of fully autonomous scenario, which we consider in here. So this will be our target goal, to achieve over 99.99% reliability. Now, the problem is that the ITS band, so the Intelligent Transportation System band at 5.9 gigahertz that is devoted to V2V communications, is actually insufficient, taking into account all the possible applications that need to be realized with V2V communications. So for current 4G and 5G basic system, basic applications, of course, maybe it might suffice, but the introduction of other services like the platooning communications may cause too high congestion of the channel, of course, and too low reliability of communications. That's why we need to look for other opportunities, and that's why we introduce here the vehicular dynamic spectrum access, short VDSA, where we try to offload the intra-platoon messaging traffic from this ITS band to alternative frequency bands, so-called frequency white spaces, for example, the white spaces in the TV bands, so TV white spaces. And in order to facilitate that, we envisage the use of radio environment maps, which will support the VDSA process, which are simply systems that collect data from many different sources, like vehicles, infrastructure, and other sources, and store it in databases, and then process it in a proper way to provide information, for example, on the usage of frequency bands, the availability, and the parameters that we should use in transmission. So in our work, we consider a motorway scenario where we have motorway multiple lanes, and we have multiple autonomous platoons that move into opposite directions. These platoons use the TV white spaces band for intra-platoon communications, right? Because we focus on the TV white spaces, we can assume that also selected frequency bands are used for digital to terrestrial transmission. So we have DTD service broadcasting actually in specific bands, and we have some fixed location of DTT receivers placed around the motorway. The good side is that we know their location in our system, so we can also take advantage of their protection. Our platoon vehicles use the 802.11p standard for communications, and they communicate in TV white spaces with the band selected using this VDSA framework that we are explaining in here. Of course, in order to operate in the TV white spaces band, the platoon cars need to use the so-called dual radio, so they have double transceiver, one for the ITS band and the other for TV white spaces, so they can communicate simultaneously with the infrastructure, which is connected to the REN system, and with the other platoon cars. And because we are operating in the TV white spaces, of course, we need to take care of this primary system, which is the DTT system. So we need to protect the reception of the DTT signal at this location of DTT receivers. And for that purpose, we use the radio environment maps that help us with the selection of proper frequency band and selection transmission parameters in order to mitigate the interference to the primary system. So to the problem formulation, actually, the main problem in our case looking from the platoon perspective, is to maximize the reliability of our communications, intra-platoon communications. So we are aiming at maximization of the probability that any pair of cars in the platoon can communicate. So here we maximize it over the frequencies, available frequency bands, the minimum probability that vehicle V will transmit successfully to vehicle U. This is, of course, equivalent to maximizing the minimum SINR, and this is what will be referred later on as a conventional approach to distributed approach. So we maximize over the frequency bands available the minimum signal to interference noise ratio of all the active platoon links, so the links between vehicle V and receiver U. Right, and the SINR can be defined as a ratio of the received power, so this is the power transmitted by V, and the channel gain divided by the noise component, which comprises the additive wide variation noise, the interference from the primary system, so from DTT, and interference from other vehicles, other platoons also operating in TD white spaces. So these interferences take into account both the co-channel interference and also the out-of-band interference. This is done using the adjacent channel to interference ratio factor, weighting factor, which is simply the value between 0 and 1 that weights the received DTT power, for example, in case of interference from primary system, taking into account the distance in frequency between the channel used by DTT and the channel used by the platoon. Similarly, we define the interference from all the other platoons, all the other vehicles, so this is sum over all the other platoons. The power received from the other platoon car, we have weighted with the adjacent channel to interference ratio factor, which depends on the distance in frequency between the two bands used by the two platoons. And it is also weighted by the probability that a vehicle in platoon L transmits at the same time when vehicle U in our platoon of interest receives. So this is the definition of SINR interference. This is our main goal, to maximize the minimum SINR, but of course we need to take care of protection of the primary system. So this imposes certain constraints on our transmission, which are mostly related to transmit power that we can use. We need to protect the reception of the DTT system signal. So the DTT signal needs to be protected if the power received at a certain receiver location of DTT signal is greater than certain threshold, gamma DTT here. And then, if it's so, we need to take care that the interference from our platoon intra-platoon communication in TD white spaces is smaller than the power of DTT divided by the signal to interference ratio minimum threshold for DTT. So this is like the required threshold of SIR. We shouldn't drop below this SIR value. And in order to achieve that, apart from the conventional approach, we also consider the Qlearning based approach. So we use the machine learning, Qlearning, where of course we have some agent that responds to certain system state and select certain actions. So in our case, action is simply a selection of a specific frequency band. We have k-VDSA bands available, so we have k-VDSA actions possible for each platoon. And then each platoon determines its state based on the estimated minimum SINR levels for different of the candidate bands, right? So we calculate the minimum SINR levels in each of the candidate bands. We quantize it using our quantization levels. So here we have an example of 3 quantization levels, and store it as a tuple, right, with the values of SINR sorted in descending level. So we have configuration from different bands, for example, band 1, band 2, band 3, and the SINR is, for example, high, low, and low with the quantization levels applied. Such a tuple describes the state of our platoon. So the total number of states, assuming this quantization and k-VDSA bands available, is R plus k-VDSA plus 1 over k-VDSA. So this is the binomial coefficient. The main problem here is, of course, how to obtain the information on the SINR. And this can be done with the information provided by REM, because REM can inform us on certain parameters that are needed to calculate the SINR, such as the DTT signal power per current location, the transmit power constraint for protection of DTT, so the maximum power that we may use within the platoon, and also the information on other platoons, like the frequency band selected by the other platoons, their location, and the transmit power used by the other platoons' vehicles. So we use this information and this definition to simply update the Qtable according to the Qlearning approach, right? So this Qtable update is done based on the reward, which is simply here calculated as the average throughput for the packets received during a single VDSA period for a given receiver, right? So for each receiver, we measure the SINR for each received packet, and then we calculate the average throughput, which is upper bounded by 100 using the Shannon formula. And then we use this reward calculation, of course, to update the Qtable with the given learning rate alpha and the discount factor gamma. And knowing the updated Qtable, we can perform the action selection. So we consider here two approaches: epsilon greedy approach, which uses the exploration or exploitation mode. The exploration mode, of course, is probably epsilon, which is here 1/100. So in exploration mode, we have equal probability of each action, so selecting of each band. In exploitation mode, we select the band that provides the maximum Q value Qtable for the given state. The other alternative is to use the softmax approach, where actually we don't have the strict here division between the exploration and exploitation mode with given probability, but rather we select our action according to its probability that's calculated based on its Q values, which are weighted by the so-called temperature parameter, right? So this temperature parameter is between 1 and infinity. So it's, in our case, it's inversely proportional to the number of reward samples collected so far for state ST. So of course, if we have a low number of samples, then it goes towards the uniform distribution. If we have high number of samples for a given state, then it will go towards the greedy option. And we have verified our work here, this Qlearning approach, using computer simulation, so C++ based simulator of motorway traffic, where we considered two scenarios with 3 and 4 platoons moving on outer lanes in two opposite directions. So the scenario with 3 platoons uses only 6 cars per platoon, and this is a lower interplatoon interference scenario. With 4 cars, we have higher interplatoon interference, and we have 10 cars per platoon. So this will be much more challenging when it comes to communications. We have 5-meter car spacing in platoon, and the platoons transmit message every 200 milliseconds. We have 2 bands used by the DTT transmission, so it's at 490 megahertz and 522 megahertz, and we have 3 VDA bands available for VDSA in between these, so at 498, 506, and 514 megahertz. We use the learning rate of 1/10 for the Qlearning and the discount factor of 7/10. We consider 3 quantization levels, and we have 10 DTT receivers in the vicinity of our motorway, which need to be protected with the minimum power protection threshold -80 dBm and the DTT SIR protection threshold 39.5 dBs. And we consider 4 different VDSA configurations. So as a benchmark, the conventional distributed approach, which uses the maximization of the minimum SINR in the platoon. We have 2 configurations of epsilon greedy Qlearning, one with ideal Qtable combining, so this is like the perfect combining case, and the other one with federated learning, where each platoon reports at the end of simulation run its learned Qtable to a central entity, and then we have the mean combining of the Qtables for all the platoons considered, and then we use it for another simulations. And the last option is the softmax-based Qlearning with also ideal Qtable combined. So we have actually verified the performance of these configurations with the following performance measures. So the first one is the probability of successful reception of readers packets. We only focus on the leader-follower link just because this is the lowest quality link. It's expected to be the lowest quality within the platoon because of the distance between the vehicles. And we can see that for the 3-platoon scenario, so the one with low interplatoon interference, we have the best performance for the conventional distributed algorithm because it maximizes the minimum SINR, while the Qlearning approaches suffer from the exploration option. So as we see, the best performance among the Qlearning is with softmax, which is well trained with over 1 million samples, because then the probability of exploitation is lower. So it achieves much better performance than the others. It's close to the distributed approach, while the other approaches, for example, the epsilon greedy options, are worse. What's interesting that the federated learning provides similar results as the ideal combining. The other performance measure that we have considered is the ability to protect the primary system, right? So our goal is to keep the signal to interference ratio level of DVB-T, so the DT transmission, above the required threshold of 39.5 dBs, right? So this is the value we're looking for. And for that purpose, of course, we have applied the power control in every case to protect the DP, so with the maximum power constraint provided by the radio environment maps. And we can observe that we have similar results for all the algorithms, right? Because they will, of course, rely on the same power control. So it seems that the selection of band doesn't have so much impact on the ability to protect the primary system. And the primary system is sufficiently protected just because no more than 10 users experience slightly lower SIR, which is mostly due to the shadowing, which is not known at the REM side. In a scenario with the 4 platoons, taking a look at the probability of success of the reception leaders packets, so this is the higher interplatoon interference scenario, we can see that the distributed approach is no longer the best performer, just because it fails to cope effectively with the interplatoon interference. So we have better results here with the softmax space approach because of the lower probability of exploration, but also the federated learning epsilon greedy approach performs similarly to the distributed approach, right? So it seems that with a higher interplatoon interference, the Qlearning performs better than the distributed approach, so it has quite nice potential. What's also important is that the federated learning actually provides even slightly better results than the ideal combining, so maybe due to some averaging, we get slightly better results. And finally, the last performance measure we have considered is the average number of branches per simulation run, which somehow illustrates the effort that we have to make the cost of our VDSA. So of course, the lower the number, the better for us. And we can see actually that the lowest number is obtained here with the distributed approach, while for the Qlearning approaches, the values are slightly higher or even significantly higher in case of softmax approach. This is mostly because of this exploration option, but also with the softmax approach because of more frequent band changes to avoid the interference. So the cost is higher, but the gains, of course, here, especially in the case of 4 platoons, are much better. So to conclude my talk, the Qlearning algorithms have a significant potential actually to perform better than the conventional algorithm, especially in case of high inter-platoon interference, right? But the drawback of Qlearning here is that we have this exploration mode, which somehow negatively impacts the reception ratio. So we should avoid actually the exploration mode in case of autonomous platoon operation. So we can consider some offline training of the Q tables, for example, having a human drivers within the platoon and then exchanging the information and updating Q tables. What's also important is that the imperfect combining, so the federated learning, does not seem to negatively impact the performance. So it should not here degrade the performance of our Qlearning. However, Qlearning results in general in higher number of band changes than the conventional algorithms. So we have slightly higher cost of VDSA. So we should take some steps perhaps to lower slightly this number of band changes. And of course, this work should be further extended, right? So the extension that we might consider here as a follow-up of this investigation is, first of all, to consider different reward formulation, right? Because we focus here on the average throughput, which maybe is not the best performance measure for the reliability. So we can actually go rather for the ratio of correctly received packets to the total number of transmitted packets, which will somehow represent the reliability of communication within the platoon. The other option here is, of course, to change somehow the definition of the system space, of the state space. So we can, of course, consider more SINR quantization level, but we can also consider other factors than the SINR, or even in the simplest form, the relative locations of the platoon. And finally, a more advanced extension here of this work is to apply the deep Qlearning, where we don't have to apply actually the learning of the Q table and so on, but rather will perform the optimization on the raw information from radio environment maps, right? So there will be no need to calculate the SINR estimates, but simply the deep learning, the genetic algorithms will learn here to use the raw information, for example, on the location of platoons and their transmit power and DTT power to simply adapt to proper conditions. So this concludes my talk. Thank you for your attention. In case you have any questions, of course, don't hesitate to ask. My contact is also via email. Thank you very much.